I don't see you there.
Let me give you the pointer.
Okay. So it's 20 minutes and plus 5 for the questions. Okay. So we have our first speaker of the session, which is Casalderrey, Solana. Okay, got it. All right. Equations of non-conformal theories.
Okay, so first of all, thanks to the organizers for letting me present this work in this nice conference. And what I'm going to talk today is. Does it work now? Yeah. Okay, so what I'm going to talk about today is I'm going to take advantage of the acronym of XQCD, and instead of talking about X as extreme, I will use it as X as mutant, as in Hollywood blockbusters, and talk about something that is more or less like QCD, but not totally QCD. So the motivation of the talk is to try to understand one of the main theoretical problems in collisions, that is how one goes from some initial state of colliding nuclei, which in principle one knows of the stuff that is colliding is formed, into some final state of a quark-gluon plasma, which expands hydrodynamically and eventually breaks into particles, and that leads to the jet. So in principle, the properties of the large nuclei are under good theoretical control, or at least we can measure PDFs, and we know what is the structure of all these objects, and using things like color class condensate, we can determine many of those properties. And once we have arrived to this hydrodynamic behavior, we have modern, very sophisticated hydrosolvers that try to extract transport properties and do hydrodynamic fits to the evolution of matter. The problem is how one goes from this initial state to this final to this intermediate state, if you wish. And to do that, you have to, at least in QCD, there are different regimes in which one uses different theoretical tools, from the liberation of partons from this initial collision, very high energy collision objects, in which one usually rely on perturbation theory, to the subsequently many collisions of those partons that lead to some equilibration, or maybe an isotropization of the matter, or as it's becoming more and more popular these days, call it hydrodynamization, and I will say more words about this complicated word. And from here, one has to use also perturbative-based approach, but not exactly the same techniques that they are here. And then at some point, once this matter has arrived to something that becomes like hydro fits into a hydrosolver. So it's a sequence of different theoretical techniques to be able to describe the whole time molecule. However, what I'm going to explore today is a game in which we can, in certain set of theories, in which we can describe the whole process from initial state to final state in one framework without doing further different approximations for the different regimes, and try to explore how it happens, how this process happens in the system. The thing that we are going to use is holography, and holography has been named and the acronym ADS-CFT several times in the previous session, and at least within this holographic frameworks I will describe in the next slide, we will be able to describe all these stages up to the breakup into many particles. As long as one is happy by having some oversimplified view of the nucleus, we will not have some bound states of neutrons and protons, but some lumps of energy that collide. And as long as we have happy with an oversimplified version of the theory, instead of using QCD, we will just use one of these mutants of QCD that at least they are non-abelian HT. So, just in one slide, all the things that you need to know for holography for this talk, and most of the things that you need to know. So what is holography? Holography is just a mathematical relation between a certain set of gauge theories in a particular limit in which the coupling constant is small, the number of colors is large, but this combination of cold coupling goes to infinity. If you have a gauge theory in this limit, what the holographic framework tells you is that this is mathematically identical to a theory of gravity. And a theory of gravity has an additional dimension, which is at least one additional dimension that I'm going to call the holographical dimension. And then gravity lives in this additional space in which the 4 dimensions of where the field theory lives is just the boundary of this 5-dimensional space. And then there is a dictionary that tells you how to, if you want to solve a complicated, strongly coupled problem in the field theory, how to translate it into a much simpler, weakly coupled problem in gravity. And in particular, if you are interested in studying stress tensors, which is what I'm going to study in the rest of the talk, you only need to study the dynamics of the gravitational field. If you are interested in studying correlators of these stress tensors, you only need to study gravitational fields that go from the boundary to a certain depth in this holographic direction, and how deep it goes is basically the scale. And then, if you want to study physics of finite temperature, the dictionary tells you that you need to study horizon, or gravity space in which there is a horizon. And if you want to and there are more terms that I will not use in this talk, like studying dynamics of brains and quarks, if you want to study additional things. So the only thing that I want to say in this slide is there is a well-defined set of rules that you can use and to translate your complicated field theory problem into a simpler gravity problem. So for the rest of the talk, I will just concentrate in the dynamics of the stress tensor. So the only thing that I need to study is the dynamics of gravity. So to solve this, to understand how the energy in a collision is distributed, basically what I'm going to transform is the problem of the collision of 2 sheets of energy into a problem in numerical relativity. The only equation that one needs to solve is the Einstein equation, which is a nonlinear partial differential equation, and which, if you can manage to solve it numerically in a computer, and this is what we'll see, with some specific initial data, that is just basically the fact that I have 2 shockwave collisions, 2 shock waves colliding once against another. One can completely determine the metric associated to this collision of space, and then one uses the dictionary that I described before to extract from this metric G in this 5-dimensional space what is a stress tensor in the field theory. If you manage to complete this program, you compute the full stress tensor of the theory associated to a collision of lump of energies without approximations other than having a very large number of colors and a very small coupling in a large tooth coupling approximation. You don't need to do anything. Assume equilibrium of equilibrium, everything is given by the numerical solution. Okay? So if you sit down with this equation, you read a number of papers. Paul Chesler and Larry Jaffe teach you what you have to do. You put it in the computer and you solve it. And this is basically what you can, the kind of things that you can get. This 3-dimensional picture is the plot of the energy density of the T00 component in some units, which is basically the height of the initial lumps of energy that are associated after the collision of 2 lumps of energy that comes in this direction and in this direction. These are the initial lumps of energy. They collide at a certain time. At the time of the collision, the energy is sum, and this is this peak. There is a factor of 2. Then the colliding objects go through, and there is some amount of energy left inside, which is the amount of plasma that you form. So this is the result of the full numerical simulation. There are no approximations about hydrodynamic behavior or equilibration or anything. But the full stress tensor in this limit is after the result of the collision. Then you can start to study different things, and this is what was pioneered by Paul Chesler and Larry Jaffe. For example, you can study how well this collision is described by hydrodynamics, and then you study things like the deviation from one of the pressure, for example, the longitudinal pressure in this direction, with respect to the hydrodynamic prediction. This is what this delta PL means, divided by some thing that is basically the energy density divided by 3, that is the average pressure. And that you can start to see that very early on after the collision, this number becomes small, and if you wait till a time that is of order 1/0.63 over the temperature, the deviations of this object is less than 10%. So this means that in this system, the onset of hydrodynamic behavior occurs extremely fast, of the order of a fraction of the microscopic scale, which is the temperature. Now, in principle, you could have thought that once that hydrodynamics starts working, you are basically equilibrated. But then you can expect, because this is what you think you learn in textbooks, equilibration, hydrodynamics means local thermal equilibrium. But you can, even within this stage, go and look in more details and see that that is not the case. In particular, you can try to see when you can plot the full numerical evolution of the transverse pressure, meaning the pressure perpendicular to the collision axis, and the longitudinal pressure, the pressure along the collision axis for different widths of the colliding objects. And if I focus in the narrowest width that we managed to collide, basically what you can observe is that the difference between the pressure, the longitudinal pressure and the transverse pressure by the time that hydrodynamics is valid, which in this unit is somewhere over here, is of order 1, meaning that even though hydrodynamics should mean that you have something that is close to thermal equilibrium in the rest frame, there are very large shear corrections that take that shift the value of the longitudinal and transverse pressure with respect to from one to the other, and so in a sense you are having some hydrodynamic behavior without isotropy in the local stress frame, which is something that it is certainly unexpected if you open a textbook. If you look into the hydrodynamic codes that are used to solve to simulate heavy ion collisions, this feature is there. Hydrodynamics is applied even when the shear corrections are large compared to the zero order term. So it's certainly nice to have a theoretical framework in which this, you can see explicitly that this happens in hydrodynamics. That hydrodynamics can describe things even when anisotropies are large. And similar conclusions can be reached nowadays if you do perturbation theory. In the last 2 years, we have seen that even in perturbation theory, these large corrections occur. Now, all what I have said before is assuming that you have a conformal theory, and now I want to describe what would happen if you study some non-conformal theory. So we certainly know that QCD is non-conformal, at least close to the phase transition. There is a large change in the interaction measure, and because of the work of the gentleman, we also know that this implies that there is that must be an increase in the bulk viscosity around the phase transition, which was estimated by these people to be given by these points, which later these authors interpolated between the high temperature behavior and the Hadron effect. So close to the transition, you arrive to values of the bulk viscosity zeta to be of order over S to be of order of 0.3. And more hydrodynamic codes are nowadays incorporating this bulk viscosity corrections, which are important to understand the data. So now what we want to do is to go beyond the conformal field theory in the holographic setup and study a holographic model that is non-conformal and repeat the collision program in that case. Of course, there's an additional motivation. If you do a global fit to this beta over S and Z over S, you also get values from the global fit that arrive to order 0.3 Z over S of order 0.3. So what we decided to study this problem. What we did to write to non-conformal theory is the minimal modification of the previous problem. it's not just Einstein gravity, but there is a scalar field, and in this 5-dimensional theory, and basically we decided to do the simplest possible thing that you can do, because these numerics become complicated, and just add one single scalar with some particular potential. And this is a completely phenomenological potential that does introduce in the theory non-conformal theory, non-conformal effects. The potential is sort of inspiring through honest top-down modifications of n equal to 4 super Yang-Mills, but those are become much more complicated for numerics, so we decided to put something simple to start with. And in this way, from the point of view of the gauge theory, basically what we are doing is something that mimics an honest deformation of n equal to 4 with a dimension 3 operator. From the point of view of gravity or dual field theory, we have a dimension 3 operator. So basically what we are saying is that we have a the modeler we are studying is a gauge theory, which is a combination of a conformal theory that would be something like an equal to form with a deform operate with a deform deformed by a operator with a mass term, if you wish, lambda, which is the only parameter that enters. And then the operator is basically is a combination of terms of side by side plus other matter content that the theory has that carries down to dimension 3 operator. And this theory has a very rich thermodynamic and transport properties. Here I just show you, for example, the interaction measure. So indeed, as the lattice one, it does deviate from 0, and it goes up and down with temperature. And this is not tuned to reproduce lattice result. We just wanted something that deviated from 0 to have a non-conformal theory. And sure enough, because we have a non-conformal theory, we have a non-vanishing Ball viscosity that you can also compute. And at the same time, you have still the universal eta over s value of 1 over 4. So this is what it comes to. Now, so you take this potential, you solve the Einstein equation plus a Klein-Granberg equation, and you end up with a full stress tensor in the same way, 3D plots in the same way like in the other, and then you can start to analyze whether the full stress tensor is described like that. Now, before I tell you the final result, there is only one subtlety. That is, our advantage is that now, because we have a non-conformal theory, we have a non-trivial equation state. That means that, and that you could see from the interaction measure. And now I just want to stop for a minute and see where this interaction measure comes from. So if you look in, so we have an operator, the dimension 3 operator, and this dimension 3 operator can acquire a thermal expectation value. And this is precisely what we plot. The duality can tell you what is the expectation value of this operator as a function of temperature. Here the sub-index R just means that I got rid of some trivial NCs and pi's so that this plot looks nice. Now, this non-trivial temperature dependence is basically the responsible of the equation of state. If there is this true field theory statement, that is the trace of the stress tensor is just basically minus the source times the Beth. And in equilibrium, that means that implies the equation of state. That means that the value of the pressure in equilibrium is the energy density up to a third minus the Beth of the source of the operator plus the thermal distribution of the expectation value. And this is the combination that gives you the equation state. However, off equilibrium, this same relation tells you that if I compute the P average, which is basically just the in a collision geometry, is just the longitudinal pressure plus 2 times the transverse pressure, then this is also related to the expectation value of this Beth in the same way. And if you wish, I can think of this as the off equilibrium equation of state. Now, the system will reach the same equation of state once the value of the expectation value of O is sufficiently close to the equilibrium equation state. And to this process in which this P average goes to the average P to the P equilibrium, which is the same, that is that the expectation value of the condensate of equilibrium is sufficiently close to the equilibrium equation state condensate, I will call equilibrium. And I put it in quotation marks because we couldn't figure out a better word, but this is the precise meaning of what I'm calling equilibrium. So then you run the numerics, you look at the simulation, and you look at the different components, and then you see here I compare the transverse pressure with the hydrodynamic approximation, the full numerical with the hydrodynamic approximation, the longitudinal pressure with the hydrodynamic approximation, and then the average pressure and the approximation, and compared to the equilibrium. So what we see is that in this particular simulation at this time, the deviations from the longitudinal and transverse pressure with respect to the average pressure is less than 10%. So this is to say that is our criterion for hydrodynamics. But however, the average pressure here, it deviates from the equilibrium pressure by a significant amount, in this case 20%. Even though the hydrodynamics, I will take one more minute, even the hydrodynamics is working very well. So hydrodynamics is describing the system even when the system is not equilibrated, when there is a significant deviation from the average pressure. The situation is not generic. One can choose parameters of collision parameters in which the hydrodynamic behavior sets before the equilibration and after, depending and we do that and scan about possible values in which you can see that actually within this model they cross a particular value, and in particular we can see that we can try to estimate where the sunset is by determining the value of the bulk viscosity where this crossing happens, and this within this model is 0.025 of the Z over S is 0.025, which is much smaller than the maximum value one would get, that is from QCD, that is 0.03. So in principle, this is well within the ballpark, with the reach of experiments that equilibrate close to the transition. And since I am out of time, I will just not read my conclusions. Just say that one of the main observations of this is that one can have hydrodynamics without equilibration, and it will be interested to understand what controls actually the onset of hydrodynamics.
Okay. Thank you. Okay, we have 2 minutes for questions. Jorge?
It's more a comment when you what you showed in the earlier part of your talk was that hydrodynamics even works already when the longitudinal pressure is still negative, which is something that you can never get from kinetic theory, which is an example of what I said this morning, that hydrodynamics is an effective theory that does not require weak coupling, that can be described by Boltzmann equation, but also works in strong coupling where you have these negative pressures that you could never get in a weak coupling approximation.
Thank you. Any more questions? Huh? Okay. Wait for the microphone.
So what I understood, the way you break conformality is by putting in an explicit breaking, by putting in a sort of a mass term for a...
Yes.
Well, we know that, for example, in pure gauge theory, that comes about the breaking of conformality just comes from the conformal anomaly.
Yes.
So is there a way to do things in a way more similar to what happens in SU3 gauge theory?
Yes. Yeah. So there are ways you can actually introduce confinement in this same confinement dynamics, and the problem is that those models are much harder to solve because they mean that you have to compactify some fiducial dimension, and then the numerics become much complicated. So we started with this one because it's the simplest way in which you can introduce conformal. And we thought that what we wanted to see is what are the effects of having a non-trivial equation state within mind so much what are the microscopic details.
Okay. Any further questions?
So in your holographic models, you have this scalar potential, so which may describe the dynamics of glow condensates, something. But if you include the brain, which describe the dynamic of quarks, so the hydrodynamic equation becomes more complicated. So can you also get a similar results from this?
Yeah. So if I would want to have fundamental matter, which is that would be again much more complicated, because the limit in which things are simple with fundamental matter is when it's not back reacted, meaning that it does not contribute to the stress tensor. And here I am solving this. I mean, I really want to see the effect of the stress tensor, so it has to be back reacted. So those are again much more complicated models. But you go beyond what you can do.
Okay, let's thank our speaker again. Now we have Professor Kim.
Don't put in the pocket, that I will see it with. Okay, great. Yeah, it's the